Okay, so welcome to this segment of, I guess, my complex analysis class. And today what we're going to be talking about is the idea of a complex derivative. And in particular, what I hope to do is, through this segment and through those to come, is convince you that the complex derivative is something that's almost magical. That somehow when you pass between this world of a real variable and a complex variable, and when you generalize this idea of a real derivative to that of a complex derivative, all of a sudden, all of these almost magical things become true. So let's start with the basic definition. Okay, so we say that a complex valued function f, defined in some neighborhood of z, is complex differentiable. So this is a new thing, complex differentiable at the point z if the limit as h goes to 0, and here's the key idea, h is no longer required to track to 0 along the real axis. So it's not just real numbers hovering close to 0. H is allowed to be any complex number making its way to 0. You have f of z plus h minus f of z over h. So the formula looks strikingly similar for a derivative, the limit that you're trying to compute, except now h is allowed to be any complex number. And our goal for the next little bit is to explore what this means and what sort of what properties follow and what sort of amazing mathematics comes from this definition. Okay, so here we go. The first thing, of course, is that we should talk about some basic properties. So basic properties. And everything that I'm about to list here, these are things that you're accustomed to from the real world, and indeed, the proofs of these basic facts follow in almost exactly the same way as they would in the real case. So the first and foremost is that if f is complex, so here I'll put a little c, so complex differentiable at z, then f is actually continuous at z. And the basic idea there is again, the proof is identical. So you look up here at the definition of complex differentiability, and if this limit has any hope or prayer of existing, then since the denominator is going to 0, the numerator had better be going to 0 as well. But the statement that that numerator goes to 0 is precisely the statement that f is continuous at the point z. Now, of course, we have other basic properties, like if f prime and g prime exist at some point z, then so does f plus g prime, f times g prime, and f divided by g prime. Of course, if we're taking the quotient of f and g, then we need to make sure that we're at a point where g isn't equal to 0. And moreover, we have the sort of basic formulas that we're accustomed to. So f plus g prime is equal to f prime plus g prime. F times g prime is equal to f prime g plus f G prime, and f over G is equal to low, oops, I didn't mean to write L, low, so G, d high, f prime, minus high, d low, over G squared. All right. We also have the chain rule. So if f and g are continuous at the appropriate points, then f of g prime of c is equal to f prime of g of z times g prime of z. And also we have the sort of basic formulas that you're accustomed to. So e to the z prime is equal to e to the z. We have the basic polynomial relations, so z to the n prime is equal to n times z to the n minus 1. We have that sine of z prime is equal to cosine of z. We have that cosine of z prime is equal to minus sine of z. We have the hyperbolic analogs, so sinh of z prime is equal to cosh of z, and cosh of z prime is equal to sinh of z. And other things like, for instance, the derivative of log is 1 over z, although I want to wait a little bit to talk about that because remember that in this complex world, the definition of the logarithm function involves the argument, which is not the argument of the logarithm of z involves the argument of z. And the argument of z isn't a strictly well-defined function. It's multi-valued, and so there's a tiny bit to think about and discuss when we're talking about the derivative of the logarithm. And of course, the proofs that all of these formulas are true that I've written right here are identical to what you're accustomed to in the real world. Okay. But what I want to talk about now is, well, I really want to explore this idea of what it means to take a complex derivative, and in particular, I want to explore the consequences of the fact that this quantity that's going to 0, this h that we saw above, is now allowed to be any old complex number instead of just some real number. And in particular, we want to tease out this sort of like multivariable approach to differentiation, since we're trying to think about our functions as in this sort of like Cartesian model, as opposed to this sort of complex world, this complex model. So let's talk about the complex derivative ddz versus this sort of multivariable model, ddx and ddy. Okay, so maybe this idea will become a little bit more clear in just a moment. So here's what we should do. Let's take our function. So we have here f of z, and when we're thinking about the complex plane in this sort of Cartesian model, what we typically do is we write z as x plus I, y. So here we have our sort of real coordinate and our imaginary coordinate, and this is exactly what allows us to identify the complex plane, or complex 1 space with real 2 space, so with the real plane. So maybe we could write f of x comma y instead of plus I times y. All right. So now let's suppose that f prime of z exists at some point z. Okay, well what that means, if we come up here, is that this limit right here exists. And again, just to highlight a little bit more, this limit exists no matter how h tracks to 0 in the complex plane. So if we're thinking about this from when we first started learning about multivariable calculus, maybe in our Calc 3 class, we encountered all of these problems where your professor was trying to sort of get you to understand that there's really a crucial difference between a one variable limit and a multivariable limit. And the sort of basic examples that you usually go through in your multivariable calc classes, you think about, here if I draw, you had these problems where you were taking limits as x comma y went to 0, and usually what you would do is, oh well, maybe I'll let x track to 0 along the x-axis, sorry, let x comma y track to 0 along the x-axis, and then separately maybe you let it track to 0 along the y-axis, and if that didn't solve your problem, maybe you tried some other slightly screwy curve. But let's try and apply these exact same ideas to the situation at hand. So if f exists, then, well, f prime of z is equal to the limit as h goes to 0, except now, like we see up here in the sort of upper right, let's let it track in just along the real axis, so along this sort of blue part. So let's say h is a real number. So then we have f of z plus h minus f of z over h. And if the limit exists, then this limit must also exist, and the two have to be equal. That's a consequence of the definition of complex differentiability. Well, let's take an opportunity to rewrite this in this Cartesian way. So this is the limit as h goes to 0, h of course a real number, and then here let's write f of, well, if h is real, then we're only augmenting the x coordinate here. And if we look, that right there is actually the definition of the partial derivative of f with regard to x. So this is partial f, partial x. And this is one of the first pretty sort of cool observations that we're able to make about this complex derivative, which is that if it happens to exist, we don't necessarily know that it exists, but if it happens to exist, then it had better agree with the answer that we would get if we went ahead and took the regular old real partial derivative of f with regard to x. Okay. So now let's try and run this same story, but now let's track in along, in this, again, this picture in the upper right, let's track in along the imaginary axis. So the red guys. So in a similar spirit, f prime of z had better equal the limit as h goes to 0, h and r. Now here what we're going to do is we're going to take f of z plus I times h minus f of z. over I times h. So this is exactly the situation where the way in which we're perturbing z is only in this sort of red direction, only along the sort of imaginary axis. Well, again, let's just rewrite this in our sort of multivariable language. Let's go ahead and pull that I, or the 1 over I out. We have the limit as h goes to 0, h in r, f of x, because we're not changing x, but we are changing y. And we already pulled that I out, so now we have the h right there. And if you look, again, what we have is precisely the definition of the partial derivative of f now with regard to y. Of course, we have to divide by I, but that's exactly what we have. All right, so let's go ahead and box that again. So what we just proved here is, again, if the complex derivative of f exists at the point z, then it must equal 1 over I times the usual multivariable partial of f with regard to y. And we can actually put these two together into a convenient form. And we see that the partial of f with regard to x, on one hand this has to equal f prime of z, on the other hand this also has to equal 1 over I times the partial of f with regard to y. And this right here is called, this has a special name, this is called the Cauchy-Riemann equation. Wow. Usually people would call this the Cauchy-Riemann equations, and they might typically be written in a slightly different fashion. So to understand what I mean by that, recall that here we have f of, now we're already thinking about this as f of x, y. Well, but we could break f into its real and imaginary parts. So that's, we could write the real part as u, and the imaginary part is v. And then, we might think about this as u of x comma y, v of x comma y. So again, here we're taking just a strictly sort of multivariable approach to what f is. And in this case, the Cauchy-Riemann equations become simply partial u partial x is equal to partial v partial y, partial v partial x is equal to negative partial u partial y. So here all we're doing is splitting things up into we're basically just splitting f into its real and imaginary parts and splitting the Cauchy-Riemann equations into their real and imaginary part. So these are, of course, like I said, the same thing. All right. Now, what I want to do now is I want to explore the converse. So, right. So where are we? We supposed that f was complex differentiable at z, and what we proved is that if f happens to be complex differentiable at z, then at z, this Cauchy-Riemann equation has to be satisfied. And what I want to prove is that this is actually not just a necessary condition, but also a sufficient condition. So what we'd like to do now is suppose that we have some complex value function f which happens to satisfy the Cauchy-Riemann equation, then I want to prove that it's actually complex differentiable. So differentiable in the complex sense, not just in this multivariable sense. So now let's talk about the converse. Okay, so let's suppose that f is differentiable in the multivariable sense. And so what this means is that both partial derivatives, so partial f partial x and partial f partial y, exist at the point z equals xy. But not just that, it's that they also provide coefficients for a good linear approximation of f. So in other words, partial f partial x and partial f partial y exist and provide good linear, provide coefficients for at. So I'll put this equals in quotes, z equals x comma y. Right, so it's x plus iy, but let's just write x comma y. So this second idea might not be something you're totally familiar with. So let me just take just a quick moment to digress about that. So here, this is kind of like an aside. So linear approximations are these things that are very often talked about in a calculus class. So you usually do problems, so you'll encounter problems of the form, compute the linear approximation to f of x at the point x naught. And maybe you're even asked, and something like, and use that to approximate the value of e to the 0.0001. But you're not usually really given guidance about how linear approximations and derivatives are related. So again, the idea behind a linear approximation, so say we have some function f of x, then if we want to compute the linear approximation at x naught, so everyone has their own notation, maybe I'll just write L of x for the linear approximation is equal to, well, here, let me just draw a quick picture. Right, so here, say, is f. And maybe here is this sort of picture of what the linear approximation should look like. And here's our point x naught. Well, certainly L should equal f at x naught. So this is f of x naught. And the slopes should agree. That's what we would mean. So, oops. So plus, well, f prime, of course, is the definition of slope. So f prime of x naught times x minus x naught. Now, so in some sense, this is sort of the definition of this is sort of how we think about f prime in terms of a slope of f. But really, it's this idea that the linear approximation actually approximates f that allows us to really talk about and think about slopes of functions. So the statement that f prime of x naught is the, quote, slope of f at x naught is what we're really saying is that if I consider this linear approximation, that it's actually a pretty darn good approximation to f at that point x naught. So here, let me try and sort of put that into words. So the statement that L is a good linear approximation to f at x naught means that if I took a limit as h goes to 0 of f of x naught plus h minus, so I take the difference between the two, I'm trying to compare them, L of x naught plus h divided by h, that this particular quantity should be going to 0. That's what it would mean for L to be providing a good linear, so that's what this h down here is, a linear approximation to f. Now, of course, this gets promoted to functions of 2 or more variables. In that case, we would write f of, say, x comma y, and then we would be taking an approximation at x naught, y naught, and our linear approximation would be a function of 2 variables, x and y. So it would look like f of x naught, y naught. And now we would have 2 slopes that we're thinking about. Partial f, partial x evaluated x naught, y naught, times x minus x naught, plus now partial f, partial y, again evaluated x naught, y naught, times y minus y naught. And just as in the one variable case, the statement that L is a good linear approximation to f at x naught, what this means is that the limit as h goes to 0 of f of x naught plus h1 comma y naught plus h2 take away L of x naught plus h1 comma y naught plus h2 over the norm of h is equal to 0. That's what it means for L to be providing a good linear approximation to f at the point x naught, y naught. And here you see these partial f, partial x, and partial f, partial y are precisely the coefficients of this linear approximation. Okay, so now let's come back to the problem at hand. So in the problem at hand, what we're now interested in is exploring this limit. So limit as h goes to 0, h is now a point in R2. Here we have, let's write this in our sort of complex notation so that we save just a little bit. So here we have z plus h minus minus now this linear approximation. So so here we're going to be subtracting f evaluated at z, and then we are going to be oh, yes, I'm sorry. So then we're also going to be subtracting partial f, partial x, times h1 minus partial f, partial y times h2. And then we're going to be dividing by the norm of h. And the statement that this is a good linear approximation is precisely that this limit is going to 0. All right. So now let's start using what we have at our disposal. So let's first observe that if this limit is going to 0, then if this limit is going to 0 with the norm of h down here in the denominator, if we trade that norm of h for the usual complex number h, that doesn't change whether or not it goes to 0. So we can trade norm of h for actual h, and here we're thinking about h as a complex number instead of an element of R2. That doesn't change whether or not this limit exists and whether or not it goes to 0. Also, right, we're assuming that the Cauchy-Riemann equation holds here. So we can also trade, right, so the Cauchy-Riemann equation says partial f partial x is equal to 1 over I times partial f partial y, but if we move that 1 over I over, we see that we can trade partial f partial y for I times partial f partial x. So we can do both of these things without changing the value of the limit. So we get that 0 is equal to the limit as h goes to 0, but now we're thinking about h as a complex number. Here we have f of z plus h minus f of z minus, now when I make the trade for partial f partial y for I times partial f partial x, now I have a factor of partial f partial x on both terms. So let me pull that out. Here I have times h1, but then we're going to be adding to that. Now I have to remember that I have this I here, so I times h2. But h1 plus I times h2, that's actually just the definition of h. So when I put this together, I see that this is the limit as h goes to 0, h and c, f of z plus h minus f of z over h. But now when I pull this other part off, those h's cancel. Partial f partial x doesn't depend on h at all. So I can separate that from the limit. So minus partial f partial x. And what we just now see is that this limit here, that's exactly the limit that we're trying to compute in the definition of the complex derivatives. What we see is not only does that limit exist, but we have an exact value for it. It's partial f partial x. Just moving that over to the other side of the equal sign. Now, of course, we knew that. That was one of the first things that we deduced, but I guess it's sort of a good reality check. Limit h goes to 0, h and c, f of z plus h minus f of z over h exists and equals something we already knew, partial f, partial x. So that's pretty darn cool. So what we just proved is that if f is complex differentiable at z, then f must satisfy the Cauchy-Riemann equations at z, and vice versa. If f is differentiable in the multivariable sense at z, and satisfies the Cauchy-Riemann equations, then it's actually complex differentiable. And that's pretty darn cool. So in future segments, we're going to be, again, exploring more and more properties of this idea of the complex derivative and later complex integration. But let's maybe stop for now. So hope you enjoyed.